Different projects sometimes happen in different ways, so maybe I will talk a bit about some of my latest projects. Um, my latest published paper is titled Linearized Stability of Extreme Black Holes. So first, what is an extreme black hole? So if you have a black hole that is either electrically charged or is spinning around its axis like the Earth and all stars do, there is a limit to how fast it can spin for a given mass. So if it is spinning at the fastest possible rate, it's called an extreme black hole. And a few years ago, I attended a meeting, the annual meeting of the American Physical Society. And it was then that I heard for the first time about new results that questions the stability of such black holes. So it is important that a black hole would be stable, because that would mean that there's actually chances that you would find someone somewhere out there in the universe. If they're unstable, if they get destroyed, then you will not be able to find them. So the stability of extreme black holes was questioned by a result by Stefanos Tsourretakis and others. And at that meeting was the first time that I heard about this, and this is one of the good things about attending conferences. You can hear about things that otherwise you would not, even though the research was published. Sometimes you miss it in the professional journals. Sometimes you can miss an article. So that intrigued me, and my first thought was, this doesn't sound right. Something there intuitively doesn't sound right, even though the results seemed to be pretty persuasive. I needed to wait a few years until a computational code that a colleague of mine at the University of Massachusetts, Dartmouth, Dr. Gaurav Khanna, was developing, was up to speed to tackle such a problem. And when that happened, I proposed, let's work on this problem of stability of extreme black holes. And we started working on it, and we found something very interesting, that a quantity that a different colleague of mine and I developed about 13, 14 years ago. It's named the radiation scalar. It was developed by Chris Bittel and myself. When we look at that quantity, then it just decays to its normal background value, even without perturbing the black hole. It turns out that if you look at quantities that all observers agree on, they all depend on a very simple way on this radiation scalar. So when we showed that the radiation scalar drops to its background value, we also showed that at the same time that all quantities that all observers agree on will also drop to their background value, which to us suggested stability. This is something which is very much in the spirit of general relativity. It's agreed upon that different observers will say different things. For example, in special relativity, you have the twin paradox. You can have a stay-at-home twin who will age much more than a traveling twin when the two compare their age upon reunion. It's accepted in relativity that different observers will measure and observe different phenomena. But there are some things that they all agree on. And every quantity that all observers agree on indicates stability. So then we started to look at what kind of observers will see unstable phenomena and what observers will see stability. And we found out that the first results that indicated instability were correct, but they are only correct for certain classes of observers, which include a very important subclass, which is observers who fall freely. So if you fall freely into an extreme black hole, you will indeed experience the instability that Stefanos Aretakis has first found. But if you have rocket engines and you adjust them in a certain way, then you will not see any instability. You will see the black hole as stable. And then we raise the following question. What do we really mean by instability? If I would say that for something to be considered unstable, then all observers, no matter how they choose to move, would have to agree on that. For example, if there is a singularity inside the black hole and some observers can go through and not be destroyed, others can, then it's not really a completely destructible singularity, because you can set your rocket engines to avoid being destroyed. And this is what we think is happening there. I think that the previous results were more specific to a particular class of observers, even though an important one, admittedly. But not all observers would share the same type of experience. So this was one example of how the progress of work happened, from first having an idea based on a talk that I heard at a scientific meeting, then waiting for the technology to be available, for the development of computational technology, then doing numerical simulations and see what happens, but then connecting it to theoretical ideas in order to draw general results, and then analysis of those and drawing conclusions. So it's a multi-step. In this case, it was over a good number of years. And it's not necessarily typical. Other projects can happen in different ways. My latest one, so it is already accepted for publication, but not yet published. It will probably published either towards the end of this month or next month. It's a project, it's a paper titled Physical Objects Approaching the Cauchy Horizon of a Rapidly Rotating Kerr Black Hole. This research is related to projects that I've been doing since the mid-1990s. My PhD dissertation was about the internal structure of black holes, mostly, which means the singularity structure inside black holes. This particular paper, the new one, is about tidal deformations on physical objects like a spaceship that falls inside the black hole. Tidal deformations are closely related to ocean tides. The reason why we have ocean tides is that if this is the moon and this is the Earth, the close side of the Earth to the moon experiences a stronger gravitational pull than the far side from the moon. This difference in the gravitational pull of the moon is what gives rise to ocean tides. So it will budge both away towards the moon and away to the moon. There are of course more effects, such as lagging because of tidal friction, because of frictional effects, etc. But the basic idea of tide is because of the difference between the gravitational pull on two sides. So you have high tides in the direction towards the moon, the direction away from the moon, and low tide in the two transverse directions, in the transfer directions to that. Same thing happens when you fall inside a black hole. Let's say that you jump feet in. Your feet are closer to the center of the black hole than your head is. So the gravitational pull at your feet is greater than at your head, which means that you will have some tidal stretching there. At the same time, you will experience tidal compression in the two lateral directions. So what would happen is that if you fall into the black hole, you would be stretched in one direction, squeezed into other. It is sometimes semi-colloquially called spaghettification. And when you fall into the center of a black hole, it would be infinitely strong. So it will be infinitely strong spaghettification. So of course, any physical object that can sustain only finite stresses would be torn into pieces, would be completely pulverized. Or at least that is the common way to think about what would happen to an astronaut or a spaceship that falls inside a black hole. It turns out that not all singularities inside black holes are born equal. And the singularity that I just described with complete pulverization is only for the simplest kind of black hole. A black hole that is exactly spherically symmetric, that doesn't have any spin angular momentum like all astronomical objects would have. But if you let the black hole spin about its axis, the singularity is of a completely different type. It is milder, it is gentler, it is subtler, in the sense that the tidal force upon arrival at least a sector of the singularity is finite. I mean, the tidal force is infinite, but then if you integrate it over the time that you approach the singularity, the total tidal deformation would be finite. This is what we showed for the first time in this paper. It has been shown before for spherical black holes that are endowed with electric charge, but it hasn't been shown yet until this paper for a spinning black hole. The reason it is harder with a spinning black hole is that the tidal deformation oscillates. So upon approach, I mean, you oscillate, but the amplitude of the oscillation changes. And we were able to show that if you integrate this effect all the way to the Cauchy-Rosen singularity, you end up with a finite total deformation, and even more so, the greatest deformation happens even way before you arrive to the singularity. And then we calculated it for a number of common materials. So what can a spaceship be made of? So it could be made of steel with maybe sapphire windows. So we looked at common materials that we could conceive that a spaceship would be made of. So they would have different resonance frequencies, different properties of material. And we specifically looked at those, what would happen to those, but the approach, of course, can be used for any material that you can think of. And it was just accepted to publication in the Physical Review last week, and probably will appear either towards the end of this month or next month. So that was a completely different process. It's something that I've been thinking about for a long time, since the mid-90s. So I would say think about it for 25 years, say. And it's not a completely solved problem, even after so many years. And I'm, of course, not the only person who is working on things like this. There has been gradual progress over the years. Admittedly, many people are not finding this research were not finding this research direction very exciting, because most funding in the field was directed toward gravitational wave detection. So people were working either with little or no funding in order to progress this research direction. But there has been gradual progress over the years. And sometimes we just think of new ideas, new ways, but the problem is not fully solved. Every time you understand something, but then you see, okay, but there are other things that we haven't thought of before. For example, until 1998, we did not know that the expansion rate of the universe accelerates. So people were thinking mostly about black holes in what is called in asymptotically flat space-time, in a universe that expands, but the expansion rate does not accelerate. And traditionally, this is what people are looking at. But now that we know that the universe has an accelerated expansion rate, it opens a new viewpoint on what happens inside black holes. It turns out that there is an intimate relationship between the acceleration of the expansion rate in the universe and what happens inside the black hole. It matters that the acceleration rate of the expansion rate of the universe accelerates. And new results are found there, things that we were not thinking of before. So it's a never fully solved problem. And it reminds me of something that Henri Poincaré, a great French mathematician of the late 19th, early 20th century, said. He said that a real problem, a true problem, is never completely solved. It's always more or less well solved. A true problem, you can always look at it from a different angle. You can always say, okay, we looked at this, but now it only opens new questions. And this is something which is typical to science. We never completely understand anything. Every time that we answer a question, it's only to open 10 new questions, questions that we didn't even know to ask before we answered the first time. So if you like, in science, we're always in a state of perpetual ignorance. But it's a special kind of ignorance. It's ignorance that you always know more, only to understand that there's even more yet to understand. And this is one of the things that I find exciting about science.